Thank you for joining us today. For those of you that are here and you've already chimed in on the Q&A and letting us know that you can hear us, I appreciate that. So again, I want to thank you for attending our webinar today. My name is Tim. I will be your host. The presentation will be about 1 hour, including a Q&A session with Matt after the presentation. So you can submit your questions during the presentation or after. You'll see that Q&A icon again on the left-hand side of your screen. Just click on that and submit your questions at any time. So now I'd like to introduce our speaker today, Matt Williamson. Matt is the Director of Engineering at ADF. He has over 30 years of process engineering and project management experience. Matt's been published multiple times in magazines and is an internationally recognized expert on combustible dust and related regulations. He's led several projects for clients to conduct post-disaster explosion investigations, implement plant recovery strategies, develop process safety management redesigns, and developed facility PSM policies and procedures. As a leader at ADF, Matt guides a team of engineers on a variety of process development and improvement projects in the food, feed, bioscience, and consumer product industries. Matt studied at the University of Kentucky, earning a degree in chemical engineering, is a licensed professional engineer, and is a member of the American Oilseed Chemist Society. So with that, I will now turn it over to Matt for today's presentation.
Okay, thank you, Tim. Today's presentation is regarding NFPA 652, the regulations that have been developed for combustible dust, how they impact your businesses. Particularly, we do work primarily in the food, feed, bioscience, and consumer product industries. However, we have also conducted DHAs in the woodworking and plastics industries as well. So we have some experience with that. Here you see a couple of my favorite photos. As you'll see, Didion is the photo on the left. This was the facility, corn milling facility in Wisconsin in 2017. This facility experienced a fairly catastrophic, as you can see, explosion that began with sparks in a corn grinding mill that spread to a dust collector that was located central to the packing area. On the right is the very well-known Imperial Sugar explosion from 2008. So what is NFPA 652? NFPA 652 is the standard on the fundamentals of combustible dust. This was developed by NFPA with cooperation from OSHA. Originally, OSHA was going to develop its own standard for combustible dusts. However, it was decided to leave this to the experts in fire protection, that is NFPA. They issued this standard on September 7th in 2015. It was intended to become effective over a course of 3 years. As that 3 years was about to expire, they extended that out to 5 years. And we'll talk about the deadline and what that has meant for you. So the purpose of this standard is to establish the relationship, the hierarchy between existing industry-specific combustible dust standards. Of course, there were multiple standards covering different industries, but it was essentially for the same hazard. And regardless of the industry that you're in, although there are some unique characteristics, the combustible dust requirements are essentially the same. So it was fairly inconsistent from one industry to the next, and it was decided to have one overarching standard to cover combustible dust across all industries. Really, NFPA 652 didn't create much that was really new. The main thing that it created was a new rule to have a dust hazard analysis, or DHA. OSHA has not formally adopted 652 as code. However, they did implement a national emphasis program back in 2007 that was targeted primarily at grain milling, but it has since been applied to other industries. It allows them to perform random inspections of facilities and implement heavy fines for non-compliance. And the standard that they, of course, have been following has been NFPA 652, and as that was its intent, OSHA has in fact been issuing fines and citations, fairly sizable citations for non-compliance with this regulation. And although they haven't adopted it as a code, they are using the general duty clause, which allows them to do that. So some of the key standards, particularly in the food and feed industries, NFPA 661 is what that industry has largely followed. And that standard has since been modified to reflect back NFPA 652 and the requirements from it. They've been consolidated somewhat. And the other key standard, 654, which is the catch-all standard for a variety of industries that are not covered under the other standards. 68 and 69 are two of the standards that involve sizing of equipment and requirements for explosion prevention systems. So the dust hazard analysis, this is what's really new. And what is a dust hazard analysis? This is similar to the process hazard analysis that was developed from OSHA's PSM program, and that was found to be very successful. So the regulations are intended to copy that success, and the DHA was developed with intent to be very similar to the process for a process hazard analysis. However, there are quite a few differences, some fairly subtle. Once you start conducting a DHA, if you've been through a PHA, you can quickly tell where the differences are. Key thing here is that this is required for all facilities. All facilities that generate, process, handle, or store combustible dusts. That includes all grain elevators, corn milling plants, oil seeds plants, but also includes plastics, places where combustible metals may be handled, such as a 3D printing facility that is dealing with metals. It also deals with woodworking facilities. So this is quite a comprehensive standard. It is retroactive in the requirement for the DHA. So that means that regardless of the age of your facility, you are required to have a DHA. Now, keep in mind, a DHA, that is just the analysis. It is a document. It is not the implementation of that document. So other components may be grandfathered, but having the DHA is a requirement. The deadline, as I've mentioned, was established for September 2020. Of course, that was last September. That deadline has passed. So what happens if you've missed that deadline? So this is the main concern. You still have time. You still need to develop that dust hazard analysis. Just keep in mind, if something happens in your facility that brings OSHA into your plant, or if OSHA decides that they're going to audit your facility for whatever reason, they can fine you. They can issue a citation now. And we have seen what they have issued in terms of citations. These can be significant. They will issue you a citation and essentially tell you to put together that dust hazard analysis. They will not necessarily shut down your plant unless they find an imminent concern, but they will cite you regardless. So a dust hazard analysis includes combustible dust data for all of the combustible dusts that you have on your site. I'll be going through each one of these criteria and what they mean. You need to identify the potential areas of risk within your facility, identify the credible ignition sources, mechanisms for suspension of dusts, safe operating ranges in your facility. What existing protection methods do you have in place today? Determination of the adequacy of that existing protection, and what explosion propagation hazards, that is, are there open paths from one piece of equipment to another where a dust explosion can spread. And you will develop at the end of the DHA additional recommendations for protection, further measures for protection, and an implementation plan. So the first step in this process is to define what you have. And NFPA 652 is very, very specific about this part of it. It is very clear that you're required in your facility to understand what the hazards are in your facility, that be communicated with operations, maintenance, those who are located on the facility, and you need to begin by defining the dust hazards that you have. Even if your facility, if you don't believe that it is a combustible dust in your facility, and many dusts are not combustible, salts generally are not combustible, most minerals are not combustible, but you need to document that, and that still needs to be communicated. But for the dusts that are combustible, and this generally applies to all organic dusts as well as most metal dusts, you need to define those dusts. So you need to identify their sources, what types of dust you have, focus on those primary hazards, which are the ones with smaller particle size, less moisture. That tends to lead to a more combustible material. You need to do sampling and testing. If you are bringing in a raw material that is a combustible dust, your supplier is on the hook for providing you with the combustibility data for that material, unless you are changing it. As soon as you process that raw material, whether it's raw corn or soybeans or whatever it may be, if you are changing it, now it's your dust. It's no longer your supplier's dust. Once it is your dust, it is your responsibility to sample that, have it tested, determine that combustibility data so that you can understand what the hazards are. So to do a proper sample, it is best to sample from the places in your facility where those dusts are accumulated. The best place for that is usually inside of a dust collector. If you can draw a sample from your dust collector, you'll need about 2 liters of material. You'll be able to get a full battery of tests. And typically you'll find, so there are different labs that can do this work. Typically it's about $3,600 per sample that you will need to have tested. You need to have a qualified lab to do that. That is something at ADF we can help you to coordinate. One of the things that I would recommend that you do, if you're not sure if your material is going to be combustible, or even if you're not sure if it's a dust. For example, if you're packaging a material that you've pelletized and you're not sure if that material is actually a dust, then you need to send a sample of it as packaged to one of these testing facilities. Do not have them grind it. If you don't tell them otherwise, they will grind it and turn it into a dust. And then of course it's going to be combustible. But what you need to know is it combustible as you are handling it? So you need to do an initial go, no-go analysis. And you may very well find out that the material as you're handling it isn't really a dust. So it will not propagate that explosion hazard. So the combustible dust data that you will, if you don't specify otherwise, you will get these 3 components, these 3 criteria. These are the most well-known. Generally, when you ask a supplier, is this dust combustible? Can you give me your combustibility data? This is what they'll give you. They will give you a KST. They may give you a Pmax. And the KST is a calculated value based on the rate of pressure rise over a given volume. What it really means is the KST is the severity of the explosion that can be developed. How big of a boom does this material make? And Pmax is the maximum pressure that can be developed in an enclosed space over that period of time. Now, the KST determines the classification and therefore determines some of the specific requirements for your facility, for your specific dust. But the KST really doesn't paint the whole picture of the hazard. It is used, KST and the PMAX are used in sizing some of that explosion protection equipment. In particular, it is used to determine the area of explosion vent panel sizing. Beyond that, that's really all that tells you. There are some more, there's some more information that you need to gather. So more you need to know. When you are testing your material, also ask for these things. NEC is the minimum explosible concentration. That's going to tell you how much dust is a hazard. So if you just have a cup full of dust in a great big silo, is that going to be hazardous? Well, not really, because you're not going to be able to reach the minimum explosible concentration. There's just not enough fuel there. MIE, however, MIE, minimum ignition energy, is the measure of the sensitivity of your dust. How easily does it ignite? And this is really one of the most important criteria that you need to find out. So if you only have a KST, you really, really need to get this value as well, the MIE, which in most facilities, you'll need to have that tested with inductance to determine the sensitivity of your material. This really tells you how easily things can go wrong. So here's a case where the lower it is, the worse it is. You want a higher number. When you go below 50 millijoules, that means that your dust can be ignited by a static spark from brush static, from equipment, if things are not properly grounded. If you go below 30 millijoules, now you are at risk of having that dust ignite from something as simple as a human spark, the kind of thing you generate on a dry winter day when you go and grab the doorknob and it shocks you. That's about 25 millijoules. So if you're going below 30, now you're in that range where you need to look at requirements for grounding your operators, especially around packaging equipment. When they're going to do work on a dust collector, they may need static dissipative flooring, static dissipative footwear. There are ways that you can deal with that, but that's a threshold that leads to that higher level of scrutiny. MIT, minimum ignition temperature. There are a couple of versions of this. MIT for a cloud, you would really only need when you're operating a spray dryer and you're concerned about how hot you can get that piece of equipment, or something like a flash dryer. MIT for a layer. This is fairly important because it sets your electrical insulation requirements. It tells you how hot can your electrical equipment get before it could spark a fire and then begin to raise the dust cloud, which could then ignite on top of, say, a motor or a light, something like that. So step 2, once you have your combustibility data and you understand how sensitive your dust is, how big of an explosion it can make, the next step is to outline the hazards. And this is where you're putting together the DHA itself. So the first thing you need to do is define the nodes for each system. And a node is just an area where dust may exist, or it may be generated, or it may leak. Define all of those nodes in your system that contain combustible dusts, and that may include the room itself, where accumulations of dust are occurring. You need to identify the free paths of travel from one area to the next, and especially identify those areas where your dust can get outside of the equipment, or where an explosion could travel beyond the equipment. A very common area that you will come across would be through blowers or fans. So, for example, in a pneumatic conveying system, When you're running a pneumatic system, the hazard is fairly light because, especially if it's a dilute phase pneumatic system, because the amount of material, you're generally below that minimum explosible concentration. But as you're shutting that system down, it becomes an issue of concern in that transition period when you're starting it up, when you're shutting it down. And an explosion in, say, a pneumatic system that goes up to a filter receiver, if there is an explosion in that filter receiver, it can travel back through the pneumatic conveying line and reach the fan or the blower, or it can travel beyond out to a fan that may be on the exit of your dust collector. And that explosion will come right out that fan or right out the air filter on the inlet to your blower. So you want to make sure that those are placed in areas that where they're not going to direct that fire toward personnel. You need to, during the DHA, you'll identify what equipment you have, what isolation you have existing, measure your indoor dust accumulations. You need to determine over a period of time, how bad does it get in between cleaning of your facility. Packing rooms are especially notorious for this, especially if you have a bagging operation. That's where you see a lot of accumulation in the area. As you conduct the DHA, the participants need to include representation from operations, from maintenance, site engineering, and of course, site safety needs to be involved as well, along with someone who offers some expertise in this area of combustible dusts. So you need to have that competent person who's available during this thing. Review each node for the likelihood, the potential for ignition sources, and so on. Document the recommendations for mitigation or potential explosions of potential explosions and their potential to spread to secondary explosions. Here is just an example. I know this is an eye chart that probably none of you can read. That's okay. This is just to demonstrate what a typical dust hazard analysis chart looks like as we're assembling it. The key thing there is that central column, which is the likelihood. If you're familiar with running PHAs, you typically have 3 columns here. You typically have severity, likelihood, and detectability. However, what you find in a dust hazard analysis is that your severity and your detectability will wash out. It's the same hazard you're looking at again and again. It really boils down to the likelihood of obtaining all 5 parts of the explosion pentagon that could be developed into an explosion. So that becomes the key criteria. In the final step in the implementation plan, you need to develop a written plan to address your combustible dust risks. That needs to have a schedule and a responsible person. That is what OSHA is looking for. They want to know that after you've conducted your DHA, what is your plan? When are you going to execute it? And who is responsible for it? And that's what they're going to hold you to. Okay, so once you have a DHA, it's this implementation plan with schedule and responsibility. That's what they hold you accountable for. That plan, however, may include further studies. You don't have to solve all of the world's problems while you're conducting your DHA. You may opt to say, we will evaluate this further, or we will do a study, but you still need to have a schedule to conduct that study. You need to have a person responsible to go and do that additional study, that additional evaluation. But that is what is then enforced. So as you develop an implementation strategy for an existing facility, you need to do this engineering review. And this is where you need to have an engineer involved to look at those high-risk areas and to help you come up with the best options for compliance, because there's almost always more than one way that you can implement this kind of redesign. Some ways may be easier to run than others, but others may be lower capital. And typically you're looking for the least expensive option from a capital standpoint. That's not always the best option, but those things need to be weighed against each other. One key thing is that you'll find, for example, explosion relief pressure, which is known as PRED, can be reduced by combining a few options. And sometimes you need to look at the combination of things like explosion venting and suppression, which are generally implemented one or the other. But there you can have that combination. So there may be some lower cost options that can be engineered. And the standard allows you to engineer some additional options, such as inerting a system. If you have nitrogen available and your bin is able to be sealed up, it may be very reasonable to put nitrogen on your bin. Weak roof design rather than direct explosion venting. This is actually commonly done for very large bins where it's impractical to put in such large explosion panels. Housekeeping is key. Housekeeping, of course, is inexpensive. It's just an operating expense, fairly inexpensive operating expense, but it's the single most critical thing that you can do for your facility. So you don't want to look like the facility you see in the picture over on the right, where you've got this dust on the floor to the point, and exactly as they say it in the NFPA standards, to the point where it obscures the color of the floor. If you can't tell what color the floor is through your pile of dust, you have too much dust. And if you walk into a packing room like the one in the top of the picture there, you want to get out. You want to get out. You don't want to be in that particular room. So it's very important to reduce your dust concentration. And the simplest way to do that is, first of all, good housekeeping. Secondly, good maintenance practices. Make sure your equipment is not leaking. Seal up those leaks. As soon as they start generating a pile of dust and powder on the outside of a rotary valve or whatever it may be, you need to get that fixed. It needs to be a priority to fix those things so that you don't develop these accumulations in the room. Because it's these accumulations that become the large secondary explosions. When something happens inside of a piece of equipment, it reaches this pile of material that gets raised into the air by the first explosion, becomes a devastating secondary explosion, which knocks down the walls and brings down the roof. You can't allow that to happen. So in the final step of this, you need to implement your solutions. NFPA 69 is very valuable for this. There's a lot of information about what you can and cannot do in NFPA 69, but it does allow quite a bit of flexibility as well. It outlines a number of options that you may have. Typical solutions, of course, include chemical suppression and explosion venting. That's what you see in the pictures here. I will say this, don't be afraid of chemical suppression. It is something that many facilities are just hesitant to implement because the first one that you install is going to come with a control system. The first one will be fairly expensive compared to the rest. So once you've got one, you might as well start putting in more because it's fairly inexpensive then to add on to that. Explosion venting is perfectly fine especially when your equipment is outside and not in an occupied area. But if your equipment, say a dust collector, is inside or in the middle of the room, explosion venting becomes prohibitive very quickly because you have to be able to vent that outside the room. And you can't do that if your dust collector is located in the middle of the room. So part of the solution may involve relocating that type of equipment. And if you can't relocate it and comparing to the cost of relocating a dust collector, a chemical suppression bottle is really a reasonable thing to do. And in that case, that's more than likely what you would want to do. You can design full containment of a piece of equipment, but for most, especially grain agricultural facilities, that's really impractical. That is something you would do when you have a very small piece of equipment and you could design that to contain 150 PSI because it's essentially no bigger than a piece of pipe. Flameless vents are something that you can do. So in that example where I talk about a dust collector in the middle of the room, you can install a flameless vent. That has certainly been done. Just keep in mind that these vents are fairly expensive and they are very large. They take up a fair amount of space, and you have to mark off an area around that flameless vent because heat and pressure does still come out of those vents. So you still have to mark off an area where your operators should not be going when the system is running. You can opt to do other engineered solutions like trying to add an inert atmosphere. However, that of course can, if you're indoors, that can introduce new hazards that can be just as dangerous, or attempting to operate below that minimum explosible concentration, which may involve some operational changes, adding things at a slower rate to a mixer, that sort of thing. So there are many low-cost solutions that can be implemented. If you are outside, something you'll often see is an explosion panel that is directed to an occupied area. To protect that, you can either relocate the dust collector, relocate the panel to another side of the dust collector, or you can simply add a deflector, which is a fairly simple solution to protect personnel from a dust collector that is outdoors. Indoors, this is still not the way to go. You need to vent that outside. Make sure that your ductwork is not oversized, and this is another common issue to when you're designing a facility, when you think, oh, well, we're going to design it for future capacity and we're going to make our ducts enormous so that we can increase our airflow in the future to double the capacity. And then that duct is just too big for your current operating rate. And what happens is that dust will begin to accumulate within the ductwork, and now that creates a new hazard. So other things you can do, passive and chemical isolation, of course, very commonly implemented. And as I mentioned, moving air intakes away from personnel. So throughout the plant, and I'll touch on a few of these areas that need scrutiny during the DHA, of course, includes your dust collectors and your bucket elevators. Those are your top two. If you look at the statistics that come from dust safety science, they will tell you very quickly more than 2/3 of all dust explosions occur in either a dust collector or a bucket elevator. So these are the main areas of hazard. Drag and screw conveyors, these don't tend to be the source of the explosions, but they can convey an explosion, particularly at those times when you are filling or emptying that equipment. Generally, when it is in full operation, you don't have a problem here because they tend to be choked with material. It's those intermittent periods where you tend to have problems. The same with pneumatic conveying systems. It's those intermediate times during startup and shutdown where you have problems. Bins and silos, I'll talk a little bit more about this. A lot goes into the size of your bin or silo. Very, very large silos, you tend not to see that protection because, for one, it's impractical, and it may also not be necessary because the larger your silo, the less likely you are to hit that minimum explosible concentration in the headspace. Hammer mills and mills in general are something that NFPA 61 pays a lot of attention to So, for example, we mentioned at the beginning of this, the Didion explosion. It was believed that that started in a corn mill. And mills are a place where those sparks can occur, where the ignition sources tend to come from. And there's a lot of air in there. There's a lot of dust being generated. All of the ingredients that you need for a dust explosion exist in a typical hammer mill. So the standards are very, very specific about the requirements around hammer mills in particular. Gravity tables, sifters, screeners, much like the conveyors, these are areas where explosions tend to travel through rather than being sourced from. But these are generally fairly wide open paths for the explosions to travel. Packaging and bagging. The problem with packaging and bagging, you generally have an open system at some point where you're filling the bags, and you will have dust accumulating in the area that requires frequent housekeeping. And most significantly, these are areas where an operator tends to be sitting or standing all the time. So you're putting your operator directly at a point where material is open, where dust is open and accessible to them. If you have a very low MIE, minimum ignition energy type material, and you're putting it into a bag and you've got an operator sitting there, you have a very, very dangerous situation that you will need to address. And truck loadout. I'll talk more about truck loadout as well. Truck loadout is notoriously difficult to maintain the dust levels. So when you're filling the top of an open top truck and you're dropping material a fair distance, 8-10 feet of free fall of large quantities of dust into a truck, it can make enormous dust clouds. And what's right in front of that truck but a big hot piece of equipment that runs that truck, the cab of the truck, the motor itself. So you need to be very, very careful. And guess what? There's often people there. So first, among dust solutions, we need to talk about isolation. As you know, the secondary explosions, those are the big ones. And the way to avoid those secondary explosions is keep the sources away from where those secondary accumulations tend to be. So if you have an incident in a dust collector, which that tends to happen, as has been pointed out, dust collectors are where these incidents tend to begin. When for whatever reason you pull up a small spark and it hits your dust collector, the dust collector's got everything it needs and it's just waiting on that spark to arrive. Once that spark gets there, you have an explosion in this dust collector. If you can contain it to your dust collector, you will likely be okay. You will lose your dust collector, but you can't allow that to go on to all of the sources that are feeding that dust collector, because that's when the problems happen. So you are required to isolate this type of equipment. This applies to dust collectors, it applies to bucket elevators, it applies to grinders and mills. You need to isolate these. Most oftenly, this is passive isolation around a dust collector. Passive isolation is usually a flap valve that will lock in place once it's activated. A flap valve is essentially a big check valve. That's really all it is. And it's fairly straightforward. There are also forms of active isolation. There's another kind of valve called a pinch valve, but most commonly that is chemical isolation. This is very, very effective. However, you do need a certain length of straight duct in or out of that dust collector before you can locate that chemical isolation device. On the outlet of your dust collector, where the material is flowing out the bottom, you also want to make sure that this is isolated. This is generally done with a rotary airlock. There are a lot of very specific requirements around rotary airlocks and NFPA 69 that need to be followed. Many dust collectors out there have a large open bottom where you attach a tote or a drum directly to the bottom of it. Just keep in mind that that tote or drum then needs to be able to hold whatever explosion. It needs to be able to hold the PRED, reduced pressure, that can be generated during an explosion in that dust collector. And that's not a cardboard box. Another thing that is a little bit controversial, but it's in the standards, so I want to address, the standards will allow you to avoid isolation in lines of 4 inches or less. That does not mean necessarily that an explosion cannot travel down a 4-inch line. The belief is that in a smaller line, the velocity will be high enough from an explosion that it will snuff out the flame, as you would see with a flameless vent or a flame arrestor. However, even if the flame does not travel down the pipe, heat and pressure will. And that can lead to an area where you may have an unsuspecting operator working at a piece of equipment, and here this 2 or 3 inch line is suddenly blowing a very high pressure, very hot blast of air at them. It is still not safe. So 4-inch lines don't require isolation, but you still want to make sure that the operator at the other end of that line is protected. Dust collectors in particular. Dust collectors are the big area of concern. And this is where OSHA is going to pay attention. They're going to say, take me to your dust collectors. And if they see a central vacuum system collector in the middle of your floor, your operating floor, and it doesn't have explosion panels on it, or it's not isolated from anywhere and it's larger than 8 cubic feet, guess what? You're going to face a citation. So ideally, your dust collectors should be located outside. That's because these things tend to blow up and you don't want it in the middle of your room. They're often on the roof. They need to be isolated from their sources because at the other end of that dust collector is a station with an open port where you're drawing the dust in to protect an operator, but that can be the hazard to the operator if an explosion's coming in the other direction. So you need to isolate that, whether it be passive or active. You need to isolate it from its discharge. Chemical suppression works great on these dust collectors. If you're indoors, that's the best way to do it. If you are outdoors, you need to put vent panels on. If you're indoors and close to a wall, you can vent explosion panels outside, but there is a limit to the length of the duct. And that has to do with the number of hydraulic diameters. So it has to do with the size of the piece of equipment and the PRED, reduced pressure, the pressure that can be withstood by the dust collector itself. There is another controversial rule within the standards about 8 cubic feet. If you are less than 8 cubic feet, you do not require explosion venting. However, I can tell you from experience that OSHA will still cite you if you do not isolate that equipment from its source. That 8 cubic feet was meant to protect shop vacs, which are generally 8 cubic feet. So now you'll find a lot of equipment designed at 7.9 cubic feet. You see a lot of cyclones designed for that these days. So you still need to be cautious about that. You may need to reinforce your dust collector with stiffeners to increase the pressure rating of that piece of equipment, or allow for suppression. Suppression will generally require about 3 to 3.5 psig. And older dust collectors, and especially older spray dryers, are generally not designed for that. Any spray dryers built before the 2000s, They used to make those out of tin foil. They were very, very thin, and they could not withstand any pressure at all. So we're seeing a lot of spray dryers throughout multiple industries being replaced with newer ones that can hold a little bit of pressure so that they can put explosion venting on. Bucket elevators, this is the other big area. You do not have to aspirate every bucket elevator. If you're dealing with certain larger raw materials like corn, you do not necessarily have to aspirate your bucket elevator, but it is still a good idea. If you're handling something like soybean meal, yes, you need to aspirate that piece of equipment. The best places to put that aspiration, generally you'll need something up at the head section, which is the top, and the boot section down at the bottom. And often the best place to do that for the boot is usually a little bit up, about 3 meters or so from the actual boot. You need to isolate your bucket elevator upstream and downstream, just like with the dust collector. You need to monitor the temperatures. So the key thing you're watching for in a bucket elevator is keep it from overheating. If it overheats, you can set off that explosion. They need to shut down if you go below 80% below the set speed of that equipment. The vent panels, generally along the side walls on the top of the bucket elevator, along the upper half generally. Make sure that your vent panels are not pointed at stair landings or platforms. We see that all the time, and OSHA does not like it. Bins and silos, there's been a lot of discussion amongst the dust safety people in recent months about bins and silos. This is where a lot of incidents continue to occur. Usually the head space in a large silo is too big for suppression to be effective. Aspiration is ineffective. These things, especially concrete silos, don't support the addition of explosion vents. So they're generally designed with weak roofs. But then to feed those silos, what do you end up doing? You put conveyors on top and people walk around up there. Well, that's no longer an effective emergency vent if someone's standing on it, or if there's conveyors up there. So you need to limit the access to these areas. You need to keep the roof area clean. That's very, very important. Truck loadout, as I've mentioned, is very, very difficult. Make sure you're grounding and bonding the equipment. Keep people away if you're filling a low MIE material. Watch the electrical area classification in the truck loadout area. And make sure the engine is off, because the exhaust pipes of your truck can reach temperatures 1200 degrees, more than enough to ignite a dust cloud. There are some nice spout designs out there that you might want to take a look at. The dust-controlled loading spout from Salina Vortex, they make an excellent one. That's the one with the stacked cups on the right. Or the dust suppression hopper from Sioux City Steel, as you see on the left, is very effective as long as you're loading out the same thing again and again. If you have any variation at all, those tend not to work. Loadout hoods, this is something that we do a lot of work with. In particular at ADF, the key thing here is make sure you're not trying to move your truck, because if you're trying to move your truck to fill the front and the back and you don't have multiple spouts, then you're really never going to be able to effectively reduce dust accumulation in this area. Your responsibilities as an owner: identify your hazards, design your equipment so that it mitigates these hazards. You have proper housekeeping, isolation of equipment, and you have to maintain this ongoing. Once you have a DHA, it is also your responsibility to maintain it. If you change your system, you have to change your DHA. You have to update that, just like you do with a PHA under PSM. So in conclusion, NFPA 652 is meant to cover all combustible dusts under a single unified code. OSHA is enforcing compliance. We have come in behind OSHA on a number of companies that have been cited. Your formal DHA by September, no, you've missed that date. you need to do that now. All dust need to be tested or proven non-combustible, and you will be held accountable for the implementation plan. So with that, if there are any questions, I know I've run maybe a little long.
Oh, that's okay. We still have a couple of minutes. Thank you, Matt. That is a wealth of knowledge. So we'll open it up now to questions from the audience. I'll give everyone a minute or two, and then we'll certainly stick around to answer all your questions. So again, you can do so by clicking the Q&A icon in the upper left corner of your screen. So I'll give it about a minute or so, let those trickle in, and then we'll start answering your questions. All right, so we've got a couple coming in. So first question here is, Matt, so when implementing a DHA, what are some ways to minimize the cost in existing facilities or when retrofitting? The cost in new facilities and then the cost in retrofitting existing facilities.
Well, with new facilities, it's fairly straightforward. You want to make sure you design it up front with combustible dust considerations in mind. Because it's much more expensive to retrofit an existing facility. With your existing facility, you want to make sure that your equipment can withstand the pressures of adding something like a suppression system, which is usually easier to implement in an existing facility. That may mean that you may need to reinforce your equipment and make sure you've done your work with housekeeping.
Okay. Excellent, thank you. Another one we have here is, so what is the typical cost range for a DHA effort?
If it's a small project, generally DHAs range from $7,000 to $12,000, depending on the size of the facility and the number of dusts that are involved. If you get into a larger facility, also if you're looking at a whole corn mill, then it's going to be $20,000, $25,000. So that would be at the upper end. But also don't forget the cost of doing that testing at $3,600 a sample.
Okay, excellent. And so is there a new deadline for the NFPA 652 regulation?
There is not. The deadline has passed. They let that deadline pass the second time through. So if you have not conducted your DHA for an existing facility at this point, you are late. So OSHA can come in and cite you for that now. If it is a new facility, this is something that you're going to see brought up depending on how savvy your fire marshal is during the permitting process. They're going to ask for this to get your permit.
Okay. All right, so it looks like we're right at 1 o'clock. So if there's no further questions, if you do think of anything, you can reach Matt. You can either give him a call or send him an email. And also, Matt's got a podcast coming out with Dust Science Safety on July 27th. So if you'd like to hear him discuss this topic even more in depth, you can follow us on LinkedIn, and we'll be sending that out once that is live. It looks like we have one more question that rolled in. It was just a thank you. So yes, thank you all for attending as well. So again, Matt is available if you do have any further questions, and we hope you have a great rest of your day. Thank you.
Thank you.